am Masturah, a student of IIUM. I would like to share my knowledge of photodetector in this video. In the name of Allah, let's explore the knowledge. Photodetector is a semiconductor material that use absorbed photon to liberate a bound electron for conduction. Figure 1 illustrates operation of photodetectors. The absorbed photon excites an electron from valence band to conduction band. This will leave a hole in the valence band. There are two principles of photodetectors, which are thermal detectors and photoelectric detectors. Thermal detectors convert photon energy into heat energy. Example of thermal detector is power meter. It is used to measure a temperature rise caused by the absorption of light. It can be very robust and used for the measurement of very high laser powers, but it exhibits a low sensitivity, moderate linearity, and relatively small dynamic range. Photoelectric detectors absorb photon-caused electronic transition to higher energy level and generate the mobile charge carrier. Under the effect of an electric field, these carriers move and produce a measurable electric current. Example of photoelectric detector is the photodiode, which will be explained in details in the video. The basic requirements of a photodetectors are high sensitivity at required wavelength, efficient conversion of photons to electrons, fast response to operate at high frequencies, low noise for reduced errors, compatible with physical dimensions of fiber, long operating lifetime, and insensitive to temperature variation. The key parameters of a photodetector are quantum efficiency, absorption coefficient, detector responsivity, spectral response range, noise characteristics, and response time. The quantum efficiency is the probability that a single photon incident on the device generates a photocarrier pair that contributes to the detector current. 1 is the highest quantum efficiency and 0 is the lowest. Not all incident photons produce electron-hole pairs, because not all incident photons are absorbed. Some photons simply fail to be absorbed because of the probabilistic nature of the absorption process, and some reflected back at the surface of the detector, thereby reducing the quantum efficiency further. In order to have a higher quantum efficiency of a photodetector, use anti-reflection coatings and use photodetector that have sufficiently large value of depth. Absorption coefficient is a material property, and it is a strong function of wavelength. Absorption coefficient is too small to give band-to-band absorption. If the wavelength range of photodetector can be generated is longer than the bandgap wavelength, absorption coefficient is very large. When the wavelength range of photodetector can be generated is sufficiently small, where most photons absorb near the surface of the device. The exponential decay of the intensity of the photon flux for two absorption coefficients are shown in Figure 2. Absorption coefficient is too small when the wavelength range of photodetector can be generated is longer than the bandgap wavelength. Absorption coefficient is very large when the wavelength range of photodetector can be generated when photons absorb near the surface of the device. Most of the photon absorption, 63%, occurs over a distance 1 over absorption coefficient, called penetration depth. Responsivity is the measure of the electrical output per optical input. It is linearly proportional to both the quantum efficiency and the free space wavelength. As shown in Figure 4, the responsivity increases approximately linearly with wavelength. In accordance, peaks slightly below the long wavelength limit and falls off beyond it. The quantum efficiency denoted by the dotted line for these detectors can be quite high. The main noises existed in photodetector are shot noise and avalanche noise. Shot noise caused by the photocurrent induced in a photodetector circuit comprises a superposition of current pulses each associated with a detected photon. Figure 5 shows that pulse formed present shot noise when photon and photoelectrons overlaps. Avalanche noise is caused by the randomness of the impact ionization process when shot noise is multiplied. Response time is a measure of how quickly the detector can respond to variations in the input light intensity. The response time is determined by three factors, which are drift time in the depletion layer, diffusion carrier in the depletion region, the RC time constant of the photodiode and its associated circuit. Drift of the carriers across the depletion layer, a fast process, is the transit times of the photogenerated electrons and holes across the depletion layer. Diffusion of the carriers, a slow process, is caused by the optical absorption in the diffusion regions outside of the high field depletion region, and it can last as long as the carrier lifetime. A constant electric field exists in semiconductor causes its free charge carriers to accelerate and encounter frequent collisions with lattice ions, which then cause the carriers to suffer random decelerations and resulting in motion at an average velocity. Diffusion time of carriers generated outside the depletion region. RC time constant of the circuit is the circuit after the photodetector acts like RC low pass filter with a passband. There are three main types of detectors, which are photoconductors, junction photodetectors and avalanche photodiodes. However, photoconductor will not be covered in this video. A photodiode is a metal SPN junction operated under reverse bias, whose reverse current increases when it absorbs photon. Figure 6 shows the circuit of PN photodiode, and Figure 7 will show the process of PN photodiode. In reversed bias, the amount of current that flows through the photodiode in the absence of any light, known as dark current, existed. The application of reverse voltage to PN junction will cause wider depletion region, where free electrons are attracted to positive terminal, while free holes are attracted to negative terminal. When photons fall on or near depletion region, the electrons are excited to conduction band, leaving the holes in valence band. In the depletion region, photogenerated electrons quickly drift to N side and photogenerated holes drift to P side, under the influence of the strong electric field creating photocurrent in the external circuit. Photogenerated electron hole pair near the depletion region have a chance of entering the depletion layer by random diffusion, therefore contributes a charged electron to the external circuit. Electrons and holes generated away from the depletion region wander randomly until they are annihilated by recombination. Figure 8 shows the graph of the quantum efficiency versus wavelength of various photodiodes. In ultraviolet and visible region, metal semiconductor photodiodes show good quantum efficiencies. Near infrared region, silicon photodiode can reach 100% quantum efficiency. Germanium photodiode and group 3 to 5 photodiode showed high quantum efficiencies. For longer wavelengths, photodiodes are called for high efficiency operation. The photon absorption does not require assistance from lattice vibrations for direct bandgap semiconductors. Absorption coefficient for direct bandgap semiconductors rise sharply with decreasing wavelength. The photon absorption requires assistance from lattice vibrations, photon, for indirect bandgap semiconductors. The probability of photon absorption is not as high as in a direct transition, and the absorption coefficient is not rise sharply with a decreasing wavelength as in direct bandgap. Figure 10 shows an example of responsivity of photodiode. The ideal silicon photodiode is compared to typical silicon photodiode. The typical silicon photodiodes differ totally from the ideal silicon responsivity. An avalanche photodiode is defined by semiconductor that received incoming light signal initiate an avalanche breakdown. Photogenerated carriers that are accelerated due to applied large electric field and generate more carriers via impact ionization, providing internal gain. The multiplication results in internal current gain, and the device can respond to light, modulated at frequencies as high as microwave frequencies. APD are designed to provide an internal current. Figure 11 illustrates the process of avalanche photodiode. The avalanche photodiode is similar to the PN photodiode, except that the bias applied to the avalanche photodiode is sufficiently large to cause impact ionization. A photon is absorbed by an electron, creating an electron-hole pair. The electron accelerates under the effect of the strong electric field, increasing its energy with respect to the bottom of the conduction band. The acceleration process is constantly interrupted by random collisions with the lattice, in which the electron loses some of its acquired energy. These competing processes cause the electron to reach an average saturation velocity. If the energy of electron is larger than the energy gap at any time during the process, second electron-hole pair by impact ionization can occur. The avalanche photodiode now has a current gain, introduced by the avalanche multiplication factor. The holes generated also accelerate, moving toward the left. Each of these also has a chance of impact ionizing should they acquire sufficient energy, thereby generating a Hall-initiated electron-hole pair. Ionization rate is the average number of electron-hole pairs created by a carrier per unit distance traveled. Most materials exhibit different electron ionization rates and hole ionization rates. Only silicon has a significant difference between electron and hole ionization rates. The responsivity of APD can be calculated by considering the current gain. Figure 12 shows the typical photodetectors available in the markets with specific parameters. Plasmonic focusing enables high-sensitivity quantum dot photodetectors. Is a plasmonic flat lens, bullseye structure. To concentrate and focus light into a nanoscale colloidal quantum dot photodetector, plasmonic lenses is developed to function as non-focusing resonant structures that simultaneously offer color selectivity and enhanced sensitivity. The researchers have been able to demonstrate the first colloidal quantum dot photodetector with a nanoscale footprint, the optically active area and spectral response of which is determined by the bullseye structure. The successful development of this detector represents an exciting opportunity for high-sensitivity sensing. The work was published in the New Nature Family Journal Light. science and applications. Allah reminded us in both Surah that there is no coincidence in this world. Everything happened according to His details, plans and measurements. Taking the photodetector as an example, as we go through the process of photodetector, we understand that it is exactly the same as a normal reverse bias semiconductor, but it happened only with the presence of photon. It is amazing to be able to understand how a tiny particle as photon could give a huge impact, as to change the characteristics of a normal reverse bias semiconductor. It is not a coincidence to get the photodetector when a normal reverse bias is exposed to the light. Alhamdulillah, with Akal given to us, we manage to benefit from His creation. Everything is according to His will. It is necessary for us to benefit from His creation by observing, exploring and researching. By nature, we will be amazed by the greatness of Allah, the Almighty, and then, surely we will submit ourselves to Him. Here are the list of references used to create this video. There are a total of 13 references used. Special thanks to everyone involved directly or indirectly in production of this video. Thank you.